So there is observation. uh, if phi from x naught to y naught uh, be a homotopy equivalence. Topy equivalence, that is, there exists a map psi from y naught to x naught uh, such that phi compose psi is homotopic to an x relative to x naught, and uh, psi compose phi is homotopic to I y relative to y naught. So if phi is a homotopy equivalence, then then we have phi compose psi star equal to ix star and psi compose phi star iy star. This implies what? That psi star composed phi star equal to I phi 1 x naught and phi star composed psi star equal to so this is equality, equal to this I pi 1 y naught. So we have already seen that if phi naught and phi 1 are homotopic relative to base point, some base point x naught of x, suppose phi and phi naught and phi 1, if phi naught and phi 1 are maps from x to y, in fact we should consider maps from x naught to y naught, such that phi naught is homotopic to phi 1 relative to x naught, then this phi naught star equal to phi 1 star. So this we have seen. By using that, we are concluding this. This is nothing but this. So this, from here, what we can conclude is phi star. From this, we can conclude that phi star is injective and psi star is surjective, because this is actually a bijective homomorphism, and from here psi star is injective and phi star is surjective. Thus phi star and psi star both are bijective homomorphisms, that is, they are isomorphisms. Hence, but we are interested in this phi. Hence, phi star is an isomorphism from pi 1 x x naught to pi 1 y y naught. Okay. Now suppose uh, phi is simply any map, right? So next case is phi is simply any map from x to y, right? So we are not talking about phi being map from pointed topological space x naught to pointed topological space y naught, right? We are simply taking any map phi from x to y. So this we are not considering this phi x naught equal to y naught, right? So this we are not considering, right? Then we can talk about phi being we can talk whether phi is a homotopy equivalence or not. So if phi from x to y is a homotopy equivalence, homotopy equivalence, then what about this phi star, right? What we can say about this phi star uh, from pi 1 x x naught, right? So suppose we consider a fundamental group of x based at x naught, then this will map this to pi 1 y comma phi x naught, right? Now, what we can say about whether it is an isomorphism or not, so we will say that we will see that this is actually an isomorphism, right? So we are here, we are not considering uh, map, we are not considering phi to be base point preserving map, right? Phi is just homotopy equivalence from x to y. So this we will prove. So before we start proof, we will prove one lemma. So there is a lemma. If if f from x cross I to y be a homotopy of maps from x to y, uh, and h is a path given by h t equal to f of x naught t. Then the three maps. So you can see that this we can define phi is a continuous map from here to here. So we can restrict this phi. We can consider a path H, right, which is which will be composition of two maps, right? So one is from I to x naught cross I, and then from here to y, right? So here it takes t to x naught comma t, okay, and then you apply this f. So here we can keep this, there is no problem. We can keep this capital X cross I. So t goes to x naught comma t, and then this when you apply f over this, so it will go to f x naught t, right? So this is ht, right? So ht defined is defined like this. Then the three maps in the diagram satisfy this phi naught star equal to beta h phi 1 star, where f x 0 is phi naught and f x1 is phi 1x, right? And here what is that diagram? It is this. So y1 x naught, y1 star, y1 y1 x naught phi naught star, y1 y phi naught x naught, and then there is a map beta h from here to here. So what is h? So what is h? H is a path, right? H is a path. H0 is what? Fx naught 0. This is phi naught x naught. Okay. H1 is f x naught 1 equal to phi 1 x naught. So basically, h is a path from phi naught x naught to phi 1 x naught, right? Hence, beta h, we can define an isomorphism from, so this h is a path where it is a path in y. It is a path in y from phi naught x naught to phi 1 x naught. Hence, we can define an isomorphism beta h from here to here. So we have seen how beta h is defined, right? So this is the lemma. So we'll discuss proof of it. So proof for every t belonging to 0, 1, I, we are using just simply I, we define a path ht from I to I by ht s equal to h t s. So basically this h, you can see that when s is uh, 0, ht0 is h0, and s is 1, ht1 is what? ht, right? So basically this ht is just a restriction of h over 0t. Okay, st is just this. Now let f be a loop in x at x naught, right? So what exactly we want to prove here? We have to prove that phi naught star applied over any loop class f equal to beta h phi 1 star applied over f, right? So for every loop class f in pi 1 x x naught, we have to prove that this, right? So this is actually what this one is beta h phi 1 compose f class, and this is phi naught compose f this class. Now this is by definition, this is h p1 f h inverse this class. Now, to show that this is equal to this, we need to show that this phi naught f, this is homotopic to h phi1 f. This is product of paths, this, and then h inverse. Okay. So we will define this homotopy. This homotopy we will define. Okay. So define G from I cross I to Y by G of ST equal to H times 4TS for S of, and then F. So of course there we have a homotopy F, right? Between phi naught and phi1, right? So we will use that. So this is basically F of 4s minus 1 comma t for s will be 4.5, and it is h 2t minus 2ts, s will be half and 1. So explicitly I will not explain, I will just tell means how I have constructed this. So this is yes, so in this portion I have defined this so this is basically HT, and this portion I have defined HT inverse, and in this portion I have considered this your I can say it is this composition of two maps to them. What I can say is so this is, it is not actually exactly composition of capital F and small f, but it is if you define a map from ST goes to f of s and t, and then you apply capital F, fs comma t, right? So basically in this portion I have defined so if this map, if you consider suppose H, right? So this H I have considered in this portion. So this will give a homotopy between this and this, because you can see here for t equal to 0, okay, for t equal to 0, GS0 is what? Here you just put t equal to 0. So you will have, when you put t equal to 0 here, you will have H0, right? And H0 is what? H0 is going to be phi naught x naught, right? So all this in this interval, you will have only phi naught x naught. And then uh, here what you have when you put t equal to 0, so this is basically capital F applied over this, comma 0 is nothing but phi naught F 4s minus 1, right? So, and here when you put t equal to 0, this is again H0, okay? So this is your so this is basically your epsilon phi naught x naught dot uh, basically this is phi naught uh, f uh, phi naught composed f, okay, and then dot epsilon phi naught x naught, and this is homotopic to this. We know that this is homotopic to phi naught composed f. So basically it is this, right? So this is so when t equal to 0, we have this map, right? This, and this is homotopic to phi naught f composed phi naught. So this you can verify. And when t equal to 1, you have here h 4s, right? And yeah, h4s will be in yeah. So basically there, when you consider t equal to, when you consider t equal to 1, then you will have h dot phi1 composed f this, then this is composition, this is dot, and then dot h inverse. So this is of course homotopic to this one. And you can see that when t equal to 1, it is h4s, and this is f, capital F applied over this, comma 1, that is nothing but phi1 composed f applied over 4s minus 1, and this is when t equal to 1, it is 2 minus 2s, right? So this is basically h2 into 1 minus s. So this will be actually h inverse in this interval. So when t equal to 1, GS1 will be exactly this one, and this is homotopic to this. And this, when t equal to 0, this will get this one, and this is homotopic to this. Hence, these two are homotopic. right? So this completes the proof. This completes the proof. We discuss following result. So this is a proposition. If phi from x to y is a homotopy equivalence, then the induced homomorphism phi star from x naught to y phi x naught is an isomorphism. It is an isomorphism for all x naught belonging to x. So if phi is, what does it mean? If phi is a homotopy equivalence from x to y, then means base point does not matter. Okay, base point does not matter. So so let us prove it. So by using previous lemma that we discussed, proof is simple. So let psi from y to x be a homotopy inverse of phi. Hence, phi composed psi is homotopic to identity on x, and psi composed phi is homotopic to identity on y. Now we consider following homomorphisms. Consider following homomorphisms. Phi 1 x x naught, phi 1 y phi x naught. This is phi star. And from, so phi is from x to y, so it will induce a homomorphism from here to here, and y psi is from y to x, so it will induce a homomorphism from here to phi 1 y x psi phi x naught. So this is your psi star, and from here we can again have phi star from phi 1 x phi psi phi x naught, right? So this is right clearly. This is phi star pi 1 y phi psi composed phi x naught. Okay. Now, let us see what we have. Uh, because this phi composed psi is Ix, so phi star composed psi star, right, is an isomorphism because Ix, it is this composed, this is homotopic to Ix. So we have what we can do. So what we have is, we have seen that in the previous lemma, that if phi naught is homotopic to phi 1, right, then phi naught star equal to beta h composed phi 1 star. This we have seen. So from here, because this is homotopic to this, hence by using previous lemma we have phi composed psi star, right, equal to beta h composed I. So what is the Ix star? This is nothing but, this is pi 1 so it depends on us which base point we choose, right? So I will not mention base point, right? So pi 1 x uh, small x, this is for every x belonging to x. Okay, we can write like this, where h, where here h is a path joining phi composed psi uh, x and x, right? So this we can write simply just beta h. Which implies this we can write psi star composed phi star. Okay. This implies here beta h is an isomorphism. Okay, so this is this where h is a path joining phi composed psi x and x. Now, beta h is the corresponding isomorphism. Since beta h is an isomorphism, phi star is injective. So beta h is an isomorphism. Hence, beta h is bijective. Hence, phi star is injective, and psi star is surjective. But this psi star, we don't need that. So, yeah, psi star is surjective. Now we can use this one. Similarly, psi star, this phi star composed psi star is an isomorphism, and hence psi star is injective. Thus, psi star. So from here, psi star is surjective. From here, psi star is injective. Thus, psi star is an isomorphism. Okay. Since phi star composed psi star is an isomorphism, and this psi star, so psi star is an isomorphism. So what we can do now, psi star composed phi star equal to beta h implies phi star equal to psi star inverse composed beta h. So beta h is an isomorphism, psi star is an isomorphism, hence psi star inverse is an isomorphism. So this is, so phi star is a composition of two isomorphisms, and hence phi star is an isomorphism. Since psi star inverse and beta h are isomorphism, phi star is an isomorphism. So this completes the proof.